Weisenfeld Tech presents Navigating RF and Wireless Technology Investments, a free microcourse delivering a high-level foundation for smarter RF procurement decisions. RF network purchase considerations. Purchasing an RF network and wireless solution requires navigating a complex and rapidly evolving landscape, where technical choices are closely linked to business performance and financial outcomes. For decision-makers and procurement professionals, balancing cost efficiency with long-term return on investment is a key challenge. At the same time, many legacy network technologies and protocols are becoming outdated, while newer alternatives are still evolving and not yet fully mature. This creates uncertainty around interoperability, future scalability, and the risk of investing in solutions that may not meet long-term requirements. This course provides a structured overview of the RF technology landscape, highlighting both established and emerging options. Its purpose is to support more informed, strategic, and economically sound decision-making. The course is aimed at decision-makers and buyers, focusing on high-level understanding rather than detailed technical engineering. Technology choices and business outcomes. Different networking technologies directly shape both the technical performance and the financial profile of the solution you procure, where technical characteristics and financial outcomes are closely linked. Technology choices determine throughput, latency, reliability, and coverage, which translate into the ability to meet specific use cases. The selected networking technology impacting how easily capacity can be expanded or services evolved without significant reinvestment. Mature and widely adopted technologies often provide predictable performance, lower integration risk, and a well-established vendor ecosystem, supporting cost control and stable total cost of ownership. In contrast, newer or less mature technologies may offer higher capacity or improved efficiency, but can introduce uncertainties around interoperability, vendor lock-in, and long-term support, potentially affecting return on investment. This illustration presents a structured decision-making model for purchasing an RF network solution. At its core, the model emphasizes that any investment must begin with a clearly defined use case, which drives both the technical requirements and the broader business context. On the technical side, key drivers such as coverage and propagation, capacity and throughput, latency and real-time performance, reliability, and interoperability define how well the solution meets operational needs. These factors ensure the technology is fit for purpose and aligned with the intended application. In parallel, financial considerations shape the feasibility of the solution. Elements such as capital expenditure, CapEx, operational expenditure, OpEx, scalability and upgrade costs, total cost of ownership, TCO, and return on investment, ROI, determine whether the solution is economically sustainable over its life cycle. Complementing these are legal and contractual drivers, including spectrum rights, regulatory compliance, service level agreements, SLAs, liability and risk allocation, data protection, and contract structure. These factors ensure that the deployment is compliant, secure, and commercially sound. Together, the model highlights that successful RF network procurement requires balancing three interconnected dimensions: technical performance, financial viability, and legal certainty. All grounded in a well-defined use case. Mature and future-proof RF technologies. Today's communication infrastructure spans a wide range of RF technologies at different stages of maturity. While some are being phased out and others are still emerging, a subset has proven to be both robust and future-ready. In this section, we focus on the technologies we consider mature and future-proof, highlighting how they operate, where they are best applied, and why they represent reliable long-term investment choices. Our approach is grounded in selecting technologies that are proven today and sustainable for the future. These are 4G LTE, 5G NR, NB-IoT, LTE-M, 5G RedCap, Wi-Fi 6 and Wi-Fi 7, Bluetooth, LoRa WAN, Sigfox LPWAN, Thread 6 Low WPAN, Radiolink and FWA, Starlink and satellite. Tetra, and to some extent Tetra 2, remain reliable choices today, but are considered legacy technologies. While Tetra 2 exists, its real-world adoption is limited, and industry focus is increasingly shifting from Tetra toward LTE and 5G-based mission-critical solutions. Some RF technologies remain in use but are gradually being retired as networks transition to modern standards. Due to limitations in capacity and efficiency, they are increasingly unable to meet current and future requirements. The following section outlines the RF technologies we believe are being phased out or are in decline. 2G technologies such as GSM, PDC, expected to be phased out in many regions in the coming years, but will remain in some markets, particularly for IoT applications relying on GPRS. 3G technologies such as UMTS, CDMA, CDMA 2000 already being phased out globally as operators transition to LTE and 5G. WiMAX never achieved widespread adoption, as other technologies filled the intended market space. Wi-Fi 4 and Wi-Fi 5 still widely deployed, but increasingly being replaced by Wi-Fi 6 and Wi-Fi 7, which offer significantly improved performance and efficiency. IDEN A2G-based technology specialized for voice and push-to-talk, PTT, now largely discontinued. Z-Wave and Zigbee still widely used in smart homes and industrial IoT, but no longer the dominant choice in new deployments. Tetra remains a reliable solution today, but is expected to gradually transition toward 4G to 5G-based mission-critical solutions in the future. RF technologies for the mainstream market. RF technologies today offer varying capabilities in performance, coverage, capacity, and cost efficiency. Rather than a one-size-fits-all solution, each technology has different strengths in areas such as throughput, latency, and lifecycle support. This overview focuses on technologies relevant to the broader market, widely adopted, scalable, and suitable for general deployments. Niche technologies, such as PLC, power line communication, satellite-based IoT, and other low-power or industry-specific solutions, are not covered. The following pages provide a high-level overview of mature, well-established RF technologies, along with those we consider strong, investment-ready options for the coming years. For GLTE in a 5G NR world. For GLTE provides reliable high-speed data and wide coverage through a mature and globally deployed infrastructure, supporting both mobile broadband and IoT use cases. It offers theoretical peak speeds up to 1 gigabit per second, while typical real-world throughput is around 10 to 150 megabits per second, depending on spectrum, network load, and deployment conditions. Typical use cases include voice services, mobile broadband, enterprise connectivity, fixed wireless access, and wide-area IoT applications requiring reliable coverage and mobility, as well as support for indoor deployments through dedicated antenna systems. For GLTE remains important due to significant existing investments in networks, devices, and spectrum, making it a cost-efficient and stable solution. It is important to consider national roadmaps, spectrum policies, and operator strategies. For GLTE is expected to continue as a baseline coverage layer and a complement to newer technologies for years to come. Unlocking the full potential of 5G. 5G NR is the global standard for next-generation mobile communication, delivering very high data rates, ultra-low latency, and support for a massive number of connected devices. It offers theoretical peak speeds above 10 gigabits per second, with typical real-world throughput often in the range of 100 to 1000 megabits per second, depending on spectrum and deployment. Most current 5G networks are deployed in non-standalone, NSA deployments, leveraging existing LTE infrastructure to enable faster rollout. However, the full capabilities of 5G, such as Voice over NR, VoNR, network slicing, and advanced industrial use cases, will be realized with standalone, SA deployments, which are expected to expand significantly in the coming years. 5G enables high-capacity applications such as automation, IoT, and critical communications, though challenges remain around coverage and infrastructure. It is expected to evolve as a foundation for future services, with 6G building on and complementing 5G over time. NB-IoT in the future IoT landscape. NB-IoT is a cellular technology introduced as part of 4G LTE to support large numbers of IoT devices. It is designed for applications that send small amounts of data, such as smart meters, sensors, and trackers, with a focus on low power consumption and wide coverage. It provides low data rates, typically up to 10 to 60 kbps, including strong indoor penetration. From an economic perspective, NB-IoT offers low device and module costs, and the ability to connect a large number of devices efficiently. This makes it a cost-effective solution for large-scale deployments, especially where data requirements are low and coverage is critical. Looking ahead, NB-IoT is expected to remain an important technology for massive IoT. It will continue to coexist with LTE-M and 5G, benefiting from existing 4G infrastructure and ongoing standardization support. However, its long-term role will depend on operator strategies and the evolution of 5G air-based IoT solutions, such as RedCap. LTE-M, expanding IoT use cases. LTE-M is a cellular 4G LTE IoT technology designed to support a wide range of IoT devices that require moderate data rates, mobility, and voice support. Typical use cases include asset tracking, wearables, and smart metering, where devices need reliable connectivity while maintaining good coverage. Compared to NB-IoT, LTE-M provides higher data rates, typically up to 1 megabit per second, lower latency, and full support for mobility and handovers. It also enables features such as Voice over LTE, VoLTE, making it suitable for applications that require real-time communication. Module and power costs are higher than NB-IoT, but enable broader use cases, potentially lowering overall solution costs. Looking ahead, LTE-M is expected to remain an important technology for mobile IoT. It will continue to coexist with 5G, supported by existing LTE infrastructure. Some use cases may transition toward 5G air-based solutions such as RedCap, but LTE-M is likely to remain relevant for many years. NR RedCap in the 5G IoT evolution. NR RedCap is a 5G technology designed for mid-tier IoT and industrial use cases requiring higher performance than LTE-M. It targets applications such as video surveillance, smart grid equipment, and industrial sensors. RedCap provides enhanced performance, typically tens of Mbps, up to around 100 megabits per second, though potentially with higher operational costs. RedCap will be offered in 5G standalone SA deployments, leveraging the 5G core to enable more efficient and future-proof solutions. From a business perspective, it can reduce the need to maintain parallel LTE-based IoT networks over time, while supporting long-term industrial and enterprise strategies. As RedCap adoption will depend on SA network availability. Over time, it is expected to complement, and in some cases replace, LTE-M in higher performance IoT segments, while continuing to coexist with NB-IoT and LTE-M for lower tier use cases. Wi-Fi 6 versus Wi-Fi 7 strategy. Wi-Fi 6, IEEE 802.11ax, and Wi-Fi 7, IEEE 802.11be, represent the latest evolution of wireless LAN technology, delivering improved performance, efficiency, and scalability. Wi-Fi 6 offers theoretical speeds up to 9 gigabits per second and typically hundreds of Mbps in real-world use. Wi-Fi 7 significantly increases performance, with theoretical speeds above 40 gigabits per second and multi-gigabit real-world throughput, enabled by wider channels, improved spectrum usage, and multi-link operation. It is particularly relevant for high-density, industrial, and data-intensive environments. Key drivers for upgrading from Wi-Fi 4 and 5 to Wi-Fi 6 and 7 include higher capacity needs, better spectrum efficiency, lower latency, improved security, WPA3, and more predictable performance. While Wi-Fi 7 adoption will grow, upgrades should be based on business needs and performance requirements. Wi-Fi 6 remains sufficient for many use cases, while Wi-Fi 7 provides a future-proof option for high performance. Bluetooth connectivity. Bluetooth is a short-range wireless technology operating in the 2.4 GHz band, designed for low-power device-to-device communication. It is widely used across a broad range of wireless applications. Depending on the version, Bluetooth supports data rates ranging from low-rate modes, around 125 kbps, to higher throughput modes of up to approximately 2 to 3 megabits per second. From a business perspective, Bluetooth offers a cost-effective and mature ecosystem with strong support across both consumer and industrial devices. Its low module cost makes it well-suited for large-scale deployments, particularly in consumer electronics and IoT applications. Looking ahead, Bluetooth is enabling new applications in areas such as smart buildings, indoor positioning, asset tracking, industrial automation, digital keys, and location-based services. This positions Bluetooth as a key enabler for large-scale IoT deployments. However, limitations remain, including limited range compared to cellular and LPWAN technologies, as well as potential interference in crowded 2.4 GHz environments. LoRaWAN for scalable IoT deployments. LoRaWAN is designed for large-scale IoT deployments over long distances, particularly for applications requiring very low data rates and wide area coverage, such as smart metering, environmental monitoring, and smart cities. It offers low data rates, up to 50 kbps, and operates in unlicensed spectrum, enabling flexible deployment through both public and private networks. From a strategic perspective, LoRaWAN offers low infrastructure and device costs, making it well-suited for large-scale deployments. Private network options provide full control over coverage, data, and security. However, investing in private networks also introduces risks, including responsibility for deployment, operation, and in-house competence. Looking ahead, LoRaWAN is expected to remain important for cost-efficient, non-critical IoT use cases, coexisting with cellular IoT technologies such as NB-IoT and LTE-M. Its role will continue to be strongest where coverage and cost efficiency are prioritized over high performance. Thread, emerging IoT mesh technology. Thread, 6LoWPAN, is an IPv6-based wireless communication standard designed for low-power, low data rate networks, IoT applications. Built on IEEE 802.15.4, it enables secure, low-power, and reliable communication between devices. With low data rates, up to 250 kbps, its IP-based architecture allows seamless integration with cloud services and modern IoT platforms. From an investment perspective, Thread offers strong potential by enabling interoperable and scalable solutions. However, it is still an emerging technology, and its adoption depends on ecosystem maturity and vendor support. Thread also faces competition from technologies such as Bluetooth Mesh and Wi-Fi-based solutions, as well as cellular IoT options like NB-IoT and LTE-M for wider area coverage. This creates some uncertainty around long-term positioning and standard consolidation. Looking ahead, Thread is a promising but still evolving technology, supported by major players such as Apple, Google, and Amazon. Investment decisions should be guided by specific use cases and long-term integration strategies. Wireless access as an alternative to fiber. Wireless access and radio links are widely used for broadband connectivity, enterprise networks, temporary deployments, backup solutions, and connecting remote locations where wired infrastructure is impractical or costly. These solutions operate over distances from hundreds of meters to tens of kilometers and can use both licensed and unlicensed spectrum, offering a wide range of throughput depending on technology, service, and frequency. From an investment perspective, they enable faster deployment and lower upfront costs than fiber, though long-term performance and scalability may be more limited in high-demand environments. Looking ahead, wireless access is increasingly a viable broadband alternative, with 4G and 5G becoming competitive with fiber in certain use cases. It will continue to play an important complementary role alongside fiber and cellular networks, particularly with the expansion of 5G. Satellite connectivity strategy. Satellite connectivity, including solutions such as Starlink, enables reliable internet and data services in remote, offshore, and hard-to-reach locations where terrestrial networks are unavailable or insufficient. For organizations in sectors such as energy, maritime, and mining, it supports critical operations including internet access and automation, with the advantage of rapid deployment and minimal infrastructure requirements. From a procurement perspective, satellite solutions reduce the need for network build-out and accelerate time to service. However, they typically involve higher equipment and service costs, along with considerations related to power availability, service reliability, and provider dependency. Looking ahead, satellite connectivity is expected to play an important complementary role to terrestrial networks, with ongoing improvements and integration with 5G and 6G. Key considerations remain around regulatory constraints, performance variability, and long-term vendor reliance. Tetra, reliable but facing transition. Tetra and Tetra 2 are primarily used by public safety and other mission-critical organizations. The technology is designed for highly reliable and secure voice communication, offering capabilities such as group communication, direct mode operation, and strong encryption. However, data performance is limited compared to modern broadband technologies. From a procurement perspective, Tetra is typically selected by organizations with stringent requirements for availability, control, and security needs. While it delivers proven reliability and resilience, it also requires dedicated infrastructure and comes with higher deployment and lifecycle costs, along with limited data capabilities. Looking ahead, the long-term outlook for Tetra and Tetra 2 is uncertain. Many organizations are evaluating or transitioning toward mission-critical LTE and 5G solutions, which offer enhanced data performance while maintaining required levels of reliability and security. As a result, Tetra-based systems may face gradual decline over time. Summary. This course has provided an overview of RF technologies that we consider relevant for long-term investment, with a focus on avoiding solutions that are in decline or at risk of being phased out. The emphasis has been on mature, scalable, and future-ready technologies suitable for broad market deployment. RF technology selection should focus on future-ready, widely adopted solutions, while carefully balancing technical, financial, and regulatory factors. As market conditions vary, all decisions must be aligned with local realities, business needs, and long-term investment strategy. Don't miss what's coming next. Subscribe to this channel. At Weisenfeld Tech, we're building a growing library of high-quality microcourses delivered through modern e-learning. Free, short, practical, and designed to create real value. As a subscriber, you'll get free access to these microcourses and be the first to know when new content is released. Subscribe today and explore more at www.weisenfeldtech.com.